Hello, I'm going to do a lecture today on Chapter 10 in our Conceptual Physics book. This lecture will consist of two major topics. One is projectile motion and the other is satellite motion, and they're both pretty much the same thing. So we're going to talk about how satellites are really just super fast projectiles that happen to be falling around the Earth. So the first part of my discussion is just a mind experiment. I'm lecturing in my son's room, so I have access to Nerf guns. Let's pretend this is a regular gun, and it won't fire Nerf bullets out of it, but it'll fire regular bullets. And let's pretend, while we're at it, that I have a device at the end of the barrel that as one bullet shoots out of the barrel, another bullet is dropped at the same time. So the moment the bullet leaves the barrel, the shot bullet leaves the barrel, there's a bullet that's dropped at the same moment, so that they both are traveling simultaneously from the same starting point. So here's my question, and I'm going to pause and let you think about it. If I hold the gun horizontally like this and I fire it, which bullet will hit the ground first? Will the shot bullet hit the ground first, or will the dropped bullet hit the ground first? Pause the video if you want. Think about it for a second. It's a good question. I always have different answers to the question. Some students automatically know. Some students have read the chapter ahead of time and they get it. But I want you to think about it if you haven't. Now I'm going to phrase the question, set it up two different ways and see if that helps you figure out whether you're right or not. If I fire the gun up in the air and the shot bullet travels upward and then comes down, whereas the drop bullet is just dropped to fall to the ground, which bullet will hit the ground first? The dropped bullet. If I fire towards the ground, same scenario, shot bullet fires out towards the ground, dropped bullet is dropped from this point, obviously the shot bullet's going to hit the ground first, right? So if we do it this way and the dropped bullet hits first, this way the shot bullet hits first, isn't there a position right in the middle where the dropped and the shot bullet will hit the ground simultaneously? There is. This is it. So if you hold the gun horizontal, it doesn't matter. I'm not suggesting that they're going to hit the ground in the same spot. Obviously, the drop bullet's going to fall down. The shot bullet's going to travel. We're assuming I'm in wide open spaces. I'm not in a room of a house. I'm not in my neighborhood. I'm in a big old field where the shot bullet can travel as far as it wants to travel before it lands on the ground. But assuming it has free reign to go as far as it wants, it will hit the ground at the same time as the dropped bullet, as long as the gun is fired horizontally. So what does this mean for physics? It's a physics thing, but what does it mean? It means, if I draw a little picture of my gun here, I have a bullet with a big velocity. I'm going to say Vx because that velocity is in the x direction. I have another bullet, and that bullet's just going to be dropped straight down. I'm not going to put that arrow there because the bullet is just dropped. It's not thrown downward. This bullet will travel obviously further, but this is as far as my board allows me to go. And this bullet will fall, and they're both going to hit the ground at the same time if this one just falls. So how does that happen? It happens because gravity does not care how fast the bullet's traveling horizontally. It's still going to pull the bullet down. I think I said ball, I meant bullet. Still going to pull it down, that bullet down the same distance every second as it would if it were just dropped. So if we drew a picture of the bullet at a certain time period, let's say this was 1 second that it took to go from its initial position to this position, and we looked to see where the shot bullet was, the shot bullet would be in exactly the same place. It would have fallen the same vertical distance It would not be in the same position horizontally because this one's falling straight down and that one's moving to the right. So that's the trick. They'll land in a different place horizontally, but they'll both land at the same time because those two bullets have the same change in vertical velocity. That's because gravity is not interested in how fast something's moving. It's going to act the same on every object. So gravity pulls down, just to remind you, 9.8 meters per second squared, regardless of how fast you're moving. So if you go to the edge of a tall building and you drop a watermelon off the edge of the building, we get a lot of that in the fall semester, and then you found some way to launch the watermelon horizontally off the side of the building, those two would still fall and hit the ground at the same time because gravity is not interested in the horizontal speed. Now, interestingly, whatever speed this thing has when it leaves the gun, assuming there's no air resistance, because that's what we do in physics, that speed is going to stay the same. It's going to keep that speed all the way through. It's just that y direction that's going to be changing as it falls. So it starts off with no y velocity at the top, no velocity downward, right at the point where it leaves the barrel. And then every second it's going to gain a little bit of velocity downward in the y direction. How much? 9.8 meters per second every second. So the speed of the object has no bearing on this number. Gravity's not going to sit there and think to itself, well, hold on, that cannon is really moving fast. I don't think I'll pull on it as hard as I am the ice cream cone that fell out of that kid's hand. Everything's going to fall the same distance each second and the same velocity at the end of each second, regardless of how fast it's moving in the horizontal direction. Even things that are aimed upwards are going to fall the same distance below an imaginary line. So if you take a ball in your hand and you throw that ball upward, there's an imaginary line that it would extend. That ball is going to fall and follow a trajectory below that imaginary straight line. And that distance that it falls each second matches up with the same thing we would notice here. It's going to fall the same distance below that line in the first second, even though it's on the way up. So that's where the imaginary line part comes in. Okay, let me make sure this is recording. I'm going to just hit stop, and then I can piece it together later and see if I need to do anything else. I'm just going to draw some pictures. Hang on a second. Okay, so I've drawn a more detailed picture of a ball being thrown horizontally. At the initial point where the ball's released, at the top, the ball only has a horizontal velocity, which I've denoted with Vx. It has a Vy of 0. There's no vertical velocity at the point where the ball is initially thrown. And then 1 second later, the ball's still going to have the same Vx component. That's what we call the little x. It's a component of the velocity. And the Vy is going to be bigger. Now it was 0 initially. Now it's 9.8 meters per second downward, because that's what gravity does to the velocity. Every second something falls. It pulls it down 9.8 meters per second faster each second. And then the second over here, the Vx has stayed the same. And that Vy is now 19.6 meters per second downward. And so what that does is these velocities combine in a way that they give the ball this sort of combination velocity. And that's why the path of the ball changes, and it takes this parabolic pathway as it falls, because the velocities combine to give it that curved path. Of course, we're assuming there's no air resistance here. We can also figure out how far the ball falls each second using some of those old kinematics equations. Honestly, we're not going to do any math with this part. It's just going to be conceptual. And the main thing that I want you to understand is that the horizontal and vertical, I can spell vertical, let me try again. Horizontal and vertical components of the velocity are independent. That means they don't have any relationship to each other. They are not related. The Vx is not changing, it stays the same. The Vy is changing, it's getting bigger each second. If you throw something up in the air, if you remember, the velocity decreases over time on the way up and increases over time on the way down. We have that little moment at the top where there's a direction change, and right at the top there's a V of 0. That's all stuff we covered back in September. This is all still true. What we're trying to do now is not just look at things going straight up and straight down, not just look at things being dropped like that, but think about how motion works when it's got two directions. It's called two-dimensional motion. How does that motion work, and how are those two things related? Is there any relationship between the x component of velocity and the y? And so the important takeaway is there is no relationship. They are not related. Like I said with the bullet example, that the gravity does not care how fast something's moving. It's going to do the same thing whether something is launched horizontally with a speed of 10,000 meters per second or whether it's dropped from the edge of your desk. So that's how projectile motion works. Now let's turn this into something a little bit more interesting. If this is how things move in the world, and if they're going to fall a certain distance each second, then let's make our scale a little bit bigger. I'm going to draw an Earth. Oh, that's a little drastic. Let me try to... I was trying to get it to end by the edge of the board, but that was a little bit much. Earth. And on the Earth, I'm going to place a cannon. And I'm going to fire a cannonball out of the cannon. Like that. Let's say I put a little gunpowder in there, and my cannonball has a horizontal velocity, and it goes out and it lands. And I'm like, cool, cannonballs, that's how they work. So then I repack the cannonball in there with a little more firepower. I fire it again, and I get it to go further. Did it take any longer for the cannonball to reach the surface of the Earth? Probably not. There is a little evidence here in my sketchy drawing of the Earth's surface maybe dropping away a little bit from the cannon. Obviously, we're real zoomed out here, and this is a gigantic cannon. If it were drawn to scale, really huge cannon. So we're putting on our helmet of disbelief and sort of suspending our notion of how things work in order to understand this little thought experiment. If I keep repacking the cannonball with more firepower, and every time it fires, it goes a little bit further before it hits the ground, that's because the Vx is getting bigger every time. It's still getting pulled down the same amount. It's getting that gravitational acceleration acting on it, gaining 9.8 meters per second every second. But overall, it's acting the same in each case. It's just that maybe the Earth is falling away just a little bit. If we keep up with this experiment and we keep going and going and going, eventually, is it possible that we could just get this thing going so fast horizontally that as it falls at the same rate that the Earth is falling away from it? Let's talk about what those distances and times and speeds would be. For every 8,000 meters or 8 kilometers you go, I'll do it out a little bit further. This way, that would be 8 kilometers. Again, my picture is very exaggerated, so this is going to look a little bit strange because it's not going to quite be to scale. Imagine that, something not being to scale. For every 8 kilometers you travel from the surface horizontally, the Earth falls away from you 5 meters. That's just the natural curvature of the Earth. So you can travel 8 kilometers along the Earth's surface and know that you've roughly dropped 5 meters below where you were at your previous original location. If I fire the cannonball out so fast that it can cover 8 kilometers in a second, then it's going to fall the exact amount that the Earth will be falling away from underneath it. This is because this distance here, that is the distance an object falls in 1 second. And I figured this out from my kinematics equations. You remember those? I know I said I wasn't going to make you do any, but there's the one of the kinematics equations from September. The distance something falls is related to its initial speed, the time, and the acceleration. If it doesn't have an initial speed in the y direction, then this term goes away. And then we can plug in and say 1/2 AT squared. This is 9.8 or roughly 10 meters per second squared. The second time would be 1. So 1/2 of 10 times 1 would be 5. So that's how I figured that out. If I can fire my cannonball at a speed of 8 kilometers per second, then the path of my cannonball around the Earth would match the curvature of the Earth. So let me draw this out, and now I'm going to zoom out further so we can see what this would look like. If we go all the way out, Earth, and then I draw my little cannonball up here. I mean, that's a big cannonball, big cannon. And I fire that cannon out, and it starts to fall, and it keeps falling. It's still falling. It's falling. It's falling. And it runs back into where it started. So is it weird? Yes, it's weird. It's a strange concept that a projectile, something you could throw, could turn into something that could orbit the Earth. We couldn't do it this close to the Earth because of air resistance. So the air resistance or air friction will stop this from happening. And air resistance would actually make it land somewhere. It would really, honestly, there's so much air at the surface of the Earth. If you fired it at 8 kilometers per second, it would just burn up. It would catch on fire, essentially. It's the reason why things that are orbiting Earth that come back in and re-enter our atmosphere are in danger of burning up. So air resistance creates a lot of heat. But, so this example with a cannon or launching anything horizontally near the Earth's surface is not going to work. I mean, not to mention like trees and buildings. It's like a Bugs Bunny episode, but this is indeed how it works. If you get up into space and you're out here where there's no atmosphere, so suddenly you're out here in this no atmosphere zone, you have a giant satellite, and that satellite is traveling so fast this way that it's falling and getting pulled around the Earth, and it's just that the rate of fall and the curvature of the Earth happen to be the same. It's strange to think about things orbiting as falling objects, but that's indeed what's going on. The reason that they are falling, the reason why isn't it just going off in a straight line? Do you remember what we talked about last week? The reason it's not just flying off in this straight line tangent path is because there is a gravitational force acting towards the center of the earth. The combination of the gravitational force, which is the centripetal force, and that tangential velocity that the satellite has in a tangent to the circle is combining to make this path. This is why astronauts generally feel kind of weird and achy when they're in space. I don't know if you've ridden any of the rides at Six Flags where you're falling, or any other rides around at carnivals and parks around the Southeast where you're falling. But whenever you're in a free fall situation, when you are experiencing weightlessness, I'm going to just erase a little bit of the earth and the projectile path. Weightlessness often comes with, fallness, I made up a new word. Weightlessness often comes from falling. If you're falling, whether you get stuck in an elevator and the cable breaks and you go plummeting in a very tragic way, whether you're on one of those rides, that falling that you're experiencing gives you a sense of weightlessness. What weightlessness really is not a lack of gravity. So weightlessness or falling doesn't mean there's no gravity. I just wrote FG = 0. So weightlessness or falling doesn't mean there's no gravity. It just means that something's missing. There's something that's not going on. Weightlessness really means that there is no normal force or no support force. If you are falling, say, in an elevator in a tragic kind of way, you are falling and the elevator is falling and everything's happening at once. So you're not standing at the bottom of the elevator. There's nothing supporting you. Everything's just falling. You couldn't jump up from the bottom of the elevator right when it hits the ground because you couldn't jump. There's nothing supporting you. It's a similar experience for the astronauts on the space station. They're in a constant state of free fall because that's literally what they're doing around the planet. They're falling around the planet constantly. It takes about 90 minutes to fall completely around the planet one time, which tells you how fast you're going. So that falling experience, the lack of a support force or normal force, is what makes you feel weightless. But weightlessness is kind of a poorly chosen term because you do have weight. The weight indeed is what's keeping you on that circular path of falling. But that's generally why astronauts feel kind of when they're in space. They typically throw up a lot. And even the plane that the NASA uses for training astronauts, it's called the Vomit Comet, and it's just a giant 747 type plane, and they climb up to a high altitude and then they go down, sort of like climbing a mountain and then going down the other side. And as they get to the top and they go down, they're all falling. The plane is falling and everybody inside the plane's falling. And they have this experience of weightlessness where everybody's just sort of bouncing around inside the padded walls of the plane. But it's called the Vomit Comet because a lot of people get sick and puke because you're falling for minutes and minutes on end. And it's a very unsettling feeling. Okay, so let me make sure. I think I've covered almost everything. There's one more thing I got to cover. Our last little bit for this unit, and then your test is online. It's a Google form. It'll post on G-Class. You can use your notes and your homework for this. The last topic is about orbits. This is planet X and it's an object in a circular orbit around planet X. I'm going to draw planet Y and an object in an elliptical orbit around planet Y. For planet X, you have some moon or something that's in orbit around X. It has a tangential velocity, and it has a gravitational force acting, and at all points of that orbit, because it's a nice uniform circle, at all the points they're going to be the same. The gravitational force is the same, the velocity is the same, and it's nice and uniform. So this orbit is a constant velocity, and there are no energy changes in this orbit. This is I should just label it, this is a circular orbit, just in case you can't tell from my beautiful artwork. The orbit over here is not circular. It looks more like an egg. It's an elliptical orbit. And in this type of orbit, we have some differences. When the object is over on this side, it has a different velocity than it does when it's on this side. So in general, as the object gets closer to the planet, whether it's a moon or a satellite, as it gets closer to the planet, its speed increases, and then as it gets further from the planet, its speed decreases. You can think of this in the same way you would two people that are throwing a ball back and forth to each other, and that ball goes up and comes down and then lands over here in this person's hand. The ball has a higher speed at their hands, and then it slows down, and then it gains speed coming back down. Same way that this is working. It's like somebody threw something up in the air away from the planet, it slowed down, and then it came back, changed directions, and came back. So in addition to having, let's talk about the energy, because there's not a constant velocity. The velocity is higher close to the planet, and it's lower further away. That means there are going to be changes in energy. So where is the kinetic energy going to be the highest in an elliptical orbit? It's where the velocity is the highest, because kinetic energy equals 1/2 mv squared. So we'll see a high kinetic energy right as the object, the moon or satellite, passes close to the planet. And then the kinetic energy is lower on this side of the orbit as it's further away. What does that mean about the potential energy? Did they do the same thing? Is the potential energy going to be high when kinetic energy is high? It's a little rewind back to last November and December when we did energy. No, the two are not high at the same point. One gets converted into the other. So if kinetic energy is high here, then the potential energy is going to be high over here. Do you remember what potential energy is equal to? So just to remind you, the kinetic energy is 1/2 mv squared. Potential energy is equal to mgh. There is a height right here. There's a distance from the planet Y. So it does have potential energy here. It's just got a lot more potential energy over here. So this is where the potential energy is a maximum. At all the points, just like we saw here, there's still an FG, and it's going to point towards the planet. So the interesting thing is when you're out here, your FG is actually going to point that way. So then you have these weird, everything's not perpendicular, and that's why this just stays in a circular path. When you get out here at the edges, things start acting a little strange. Then you get these weird angles, and that's what's essentially slowing your moon down and then speeding it up as it comes back around. So that's why we see a change in speed, because we have these weird vector relationships. So the main thing you'll have to know about this stuff is that a circular orbit has everything constant and uniform all the way around, but the elliptical orbit has different velocities depending on where you are in the orbit, different kinetic energy, different potential energy. And that is it. We're done with the unit. It was a lot, I know, a lot of chapters. And this is our last mechanics unit, so we won't be talking about velocities and forces and things. is, well, we'll still talk about force because we got to do electrical forces and magnetic forces. But yeah, this is it. So good luck on your test, and I will see y'all next week. Bye.